Hello, everyone. Welcome to today's presentation on using binned variables in predictive modeling. My name is Sue Hubbard. I'm a senior analytic consultant at FICO, and I'll be today's presenter. Following the slide portion of the webinar, I'm happy to answer any questions. We're going to have a rather large attendee list. So once the slides conclude and you'd like to submit a question, I'm going to ask you to use WebEx's Q&A functionality. Lastly, I just need to announce that this WebEx event is going to be recorded. Just a very short few bullet points about myself. I hold a Master of Applied Statistics degree. I have been in the field of analytic consulting for 20 years total. A strong focus I've had in my career has been on predictive analytics. And I've worked for companies such as Libra Research, American Express in downtown New York, and Infocentricity. And if you're at all familiar with Infocentricity, you'll know a large portion of us were also previous FICO employees prior to joining, and I fit in that category as well. As I bring up this slide that kind of introduces FICO analytics, I'm tempted to focus on the keywords data and decisions because it's a very accurate and concise description. FICO analytics use available data to produce the best decisions possible. But actually, I think the appropriate keyword to focus on is business. At FICO, we understand that we do not operate in the world of analytics for analytics' sake. We can't. In our world, analytic precision is, of course, the centerpiece, but it sits in this nest of constraints that absolutely must be addressed when we're solving any particular business problem. And this is where FICO analytics excels. We understand analytics in the context of business. Now, there are so many different and excellent analytic methodologies that can be brought to the table. Here at FICO, we experiment with them literally on a daily basis. But what this webinar presents is how one particular technique, that is the binned variable approach, provides not only an effective analytic solution, but it works in the context of solving the entire business problem. Okay, with that, I'd like to start off such that we're all on common ground. I'd just like to go through some commonly used model formulas, and all of them are going to be in its most simple example, a single predictor X when we're estimating a target variable Y. Probably everyone is familiar with the basic linear model. The value of X is multiplied by some singular coefficient beta, an intercept value is added, and then the predictive solution is created. On my slides, they're going to be called score. This assumes there's a linear relationship between X and the target variable Y. If it's not found in the data, typically we can put X through a transformation, any transformation G of X, log exponent squared, such that now that linear relationship exists. Our transformed value, G of X, is now multiplied by a singular beta, added to a singular intercept, and now we have our predictive solution. One step toward how we handle scorecards and scoring at FICO is rather than using the actual value of X, we transform X by creating bins and transform into weight of evidence values. And this would be for when we're in the scenario where Y is a binary outcome. So now the formula for the solution stays the same, but G of X is now more table-like. It is if X falls into a low or a medium or a high category, the value that we use is calculated as the weight of evidence value. We look at the distributions of the records in the two principal sets. We take their ratio and we take the natural log. This equation will come up later, both for weight of evidence and information value. But the idea is low values will use the value of negative, in this example, 0.47. Medium values of X now utilize 0, and high values 0.47. Not quite what we do, where we live is in the world of discrete additive models or scorecards. We bin X, but we transform them into dummy variables. And so the score formula looks a bit different. Let's say X still takes its low, medium, and high values. Now, what will be turned on are a series of on or off, a series of indicator variables. There will be a coefficient calculated for bin 1, coefficient calculated for bin 2, coefficient calculated for bin 3, and those will join the intercept value, such that scoring any particular individual or record will use one and only one of the appropriate betas. They're mutually exclusive bins, and they're collectively exhaustive. Okay, for a more formal definition with an equation, what we're out to do is score observation I. I used the very simple example on my previous pages of a single variable in the model, X. This expands it to a much more realistic scenario, which is there are J number of predictors in the model, J variables, each binned in their own appropriate fashion with K number of class levels, as depicted in the graph on the right-hand side. So each beta is going to be calculated for each bin for each variable, summed over each variable, summed over all the variables in the model, and not to forget the intercept value. Okay, so there are a number of different reasons why we choose the binned variable approach when we're building predictive models. And I'm going to address each of these in the subsequent slide. There are analytic issues, just the ability to visualize the relationship between predictor and target, particularly when we're working with a binary target variable. And what to do, how to handle or how to manage nonlinear relationships between the predictor and the target. In the category of processing issues, what binning hands us is this unifying framework for us to work on both continuous and categorical predictors, as well as for us to work with binary or continuous targets. And what's very important is we use measures that come out of this process that are invariant to the population odds if we're working with a binary target, and invariant to the population mean if we're using a continuous target. It really elegantly handles some data issues like missing or special predictor values, as well as how to handle outlier predictor values. And then just under the practical issues, some of us work where we not only have operational, but we have regulatory constraints placed on us in our quest to solve the business problem, and also the requirement to be able to compute reason codes. In financial services, if a consumer requests credit and is turned down, they by law need to be told why. And when an analytic solution or empirically derived solution is used to make that decision, those come from the model as reason codes. It's also very easy for a non-modeler to look at a scorecard and get a really good grasp of what the underlying data is saying. And it's also, most systems are already set up to deploy class models. Okay, so diving into each of the two of those. In an attempt to use an XY scatter plot to plot and understand the relationship between a predictor, a continuous predictor, and a binary target, we won't get very far when everything stacks up on our 2, 0, or 1 outcomes. But if we start to overlay the concept of binning and now aggregate the records into bins such as up to value of 32, 32 up to 38, and so on up to 62 and greater, what we glean from this is insight. If now I collect my data into these K levels, ranges, bins, classes, I, as an analyst, can keep my eye on the quantity of data that is going to fall into my two principal sets. And again, I'm looking in a binary target. It's my first example. I can see now if I'm applying sample weight, at this point I will look at the weighted percentages, where all counts are for me to convinced myself there's a substantial amount of data that the subsequent measures are going to actually be robust and something that I can rely on being repeatable. My calculation of weight of evidence now can be represented both numerically as well as graphically. And now I have a pictorial graphical representation of a predictor rank ordering my target. Okay. The interpretation of weight of evidence would be in relation to the neutral line or the 0 line. If level K is a neutral indicator, no real preponderance one way or the other of ending up in category 1 or category 0 as my outcome, you'll see a 0 value, and that's along the neutral line. The interpretation of a positive indicator, a positive number, is just a higher propensity to have the outcome or be in the outcome of the 1 category, a higher preponderance to be a 0 in the negative numbers left-hand facing bars. If we talk about binning and its handling of nonlinear relationships, if this is the actual underlying relationship of the data, a linear solution might look something like this. As I now overlay bins on top of that, I can now start to find my solution as a piecewise constant fit. Now here are the individual betas that I've calculated using all of the information inside each of these individual bins in relation to the information of the whole population. It's an analytical look at nonlinear relationships, but let me take a slightly different look at it in the next slide. This is my analytic hat, but now what about the business intelligence behind this? So I'll put up a slide. It actually comes from a real use case that I experienced with working with a customer. A very large retailer decided to tackle a target market. They wanted to bring in new parents into their store to buy all of the different items one needs when one has a new addition to the family. And so their business strategy was, let me get a mailing list. Let me assemble demographic data available for that mailing list, and I'm going to send out a coupon for the least common denominator of what every new parent needs, and that is diapers. So out went a test mailing, and back came results. And one of the pieces of demographics was age. When they plotted age against response rate to that direct mail campaign and the using of the coupon, they saw the data representing this relationship. If I took a linear modeling approach, I might come up with a solution that looks something like this. Now, from a business intelligence standpoint, I want to know something. I want to know who is my target audience. If this is my model solution and I have a single beta drawing the conclusions about the relationship between age and response, I may pass back to my business partners, your more responsive group is younger than your older group, when actually a more accurate description of the relationship is you have two completely different high responding segments to this by age. You've got the parents, where we see a peak somewhere between 35 and 39. But don't forget, you've got the grandparents also up here, somewhere nested between 55 and 64. Passing back a model to the business partners that captures the betas that actually fit this nonlinear relationship gives them this business intelligence. And what they can take away is, I might not need a single creative. I may need two completely different creatives to go out, targeting an expected new parent in my lower score range, or age range, I'm sorry, and a prospective grandparent. Two completely different messages, probably two completely different visuals as well. If we opt for the bidding approach, what it provides us is generalization in two ways. We can apply bins to either continuous or discrete alpha predictors. What in effect we're doing to the continuous predictors by binning them is turning them into a discretized version of themselves. So we can also easily supply a classer with an alpha predictor where each individual unique value will be placed in its own bin. From there, using your domain expertise, you may decide that certain values do or do not belong together, especially that would be provided by you if there's not really any ordinality in your discrete predictor. The other generalization is you can also provide a classer with a binary target or a continuous target. It'll be the exact same methodology. Take a continuous or a discrete variable and provide information on a binned level as well as a variable level. Binned level information for a binary target is much more valuable when looking at weight of evidence, the relationship between predictor and target. At the variable level, it would be information value. The sum of the bin level information values give you a condensed version of the predictive content. Everything can remain exactly the same, but your measures or your metrics will change. You'll lose the concept with a continuous target of this 1-0 principal set idea. But all you need to do is start comparing bin level means to population means. At the bin level, this can be expressed in the form of normalized mean, a difference between average and bin level mean divided by standard deviation. And then the analogy to information value would be R squared, the weighted average difference between each bin's mean and the total population mean. The binning approach also provides statistics that provide you with normalization. So those same two stats in talking about a binary target. Let's take two side-by-side cases, identical in every way except for the population odds. Case 1 has population odds 9-1, and case 2 has 10 times that, population odds 90-1. If I'm looking at metrics that go back to raw numbers, I'll be looking at metrics such as log odds or probability of 1, the total number of records falling into category 1 out of the total number of 0 and 1 records. I'm going to see two very different situations, both in total and at the bin level. When I rely on weight of evidence, as long as my distributions remain the same, weight of evidence remains completely invariant to this multiplying 10 times the population odds. I will still get the same relationship. With information value being built off of weight of evidence, we have that same concept going on at the variable level. So now when we start with our weight of evidence and multiply it by just the difference between the two distribution proportions, then we can sum the column. And now, again, we've got a statistic that's invariant to population odds when we're talking about information value, or population mean when we're talking about R squared. The value that this brings us is the availability to rank order not only predictors within a project. So let's say I am trying to figure out which variables to include or exclude from a model or where to start. I can rank order all of my candidate predictors related to my particular target variable by information value, rank order them, and start from top to bottom in my assessment and my inclusion process. I can also gain information. I can start to build up my expectations of predictive strength as I move from project to project. Example scenario would be if I've got multiple portfolios that I'm managing. As I see information values and assess their magnitude in one case, I can have a good indication of predictive strength in comparison to another portfolio in another project. A nice elegant way to handle outliers is by classing them with all of their other neighbors. So if I have an extremely high, an extraordinarily high positive value or an extraordinarily low value, it would be the same on the other end. They won't, I'll use the word artificially pull my solution in one direction or another. They'll simply be treated like all other values in the highest bin if it's a very high value outlier, or just like all of the others in the low value. So it will greatly minimize their impact. Binning can also handle both missing and special values. When you're dealing with missing values, you have a couple of options in many of the modeling solutions that you may be used to working with. One of them is if I have missing data, I need to just exclude a record. The other is I need to place on it a very large assumption that it will be pretty analogous to an average, whatever the outcome is for my average value. So imputing this to a mean or a median. What binning will allow you to do is take missing data and be able to preserve whatever predictive content might be coming along with the fact that data is absent. So in my example, I took all records that had missing for this particular variable, and I gave it a value outside of the range of valid values. Let's say this is anything that's a non-negative number or perhaps a percentage. I can safely apply missing values and redirect them to something like a -9. I can then treat this bin like any other valid bin. And in doing so, I can understand, is there predictive content associated with missing, and not leave it on the table. I can now include that in my predictive models solution. Anybody who works with credit bureau data is really familiar with the concept of special values, but let's take a different example, a marketing example. Let's say I'm looking for some kind of ratio, a percentage of purchases in a particular category. If I come up with a category of missing that's, well, there's not blank information where I'm looking for it. There's information, but the manipulation I'm trying to do can't be done because, let's say, for example, the denominator is 0. I have a different category for that to fall into. And again, I can assess, does that have separate predictive content? Probably the better example is this one, no occurrence. Let's say this is my customer base, and this variable is capturing the number of months since a customer returned an item. So if I categorize it as missing, I'm confounding it with, I really couldn't find any information. It might not yet be a customer. This one is, I've found the customer, but as I'm trying to capture the number of months, the recency since a return, I'm finding this is a group with they have never returned an item. I don't want to exclude them, and I want them to fit into the context of this variable, what information it's capturing. It's capturing information about returns. And this is my best category. It's also my largest. This is the happiest group of customers I have. If this is a purchase type of target variable, they are purchasing in the above average, and they are my largest group. Okay. And then the idea of constraints. When you're using a binned approach, there's the availability to not only pass predictors to the solution and then the objective function is going to be optimized, you can also pass the requirements for any kind of constraints on the betas that are being solved for. So for example, if I am trying to correct for an anomaly that I see in the data, and let's say I am expecting, with my domain expertise, that as I move from lower to higher of this particular variable, I know that I should see a smooth monotonically increasing pattern in whatever it is I'm capturing. With a binned approach, you can actually place constraints on the solution by stating, when the coefficient for bin 3 is being optimized, it also needs to satisfy the constraint of being less than the solution for bin 4. Bin 4 less than 5, 5 less than 6, and so on down the line. Sometimes you're in this situation where you're really just trying to enforce a pattern. Other times you're actually constrained by a regulatory issue. I have a protected group and I need to make sure by law that they receive highest awarded points in my empirically derived system. That would be regulatory issues as well. And these constraints need not be confined to monotonically increasing or decreasing. Let's say I was looking at my diaper example. I could place constraints to maintain the rise in response that I saw in the new parent age range and my rise in response that I see in the grandparent age range. So constraints are really just a comparison of adjacent bins, but they can go in any direction. You can maintain a singular monotonically increasing or decreasing pattern. You can reinforce a U-shape. You can even reinforce that bimodal shape if wanted. Okay, there's also the availability to neutralize a bin. So make sure that when the solution is being calculated, that a particular bin of your choosing does receive neutral points, just as what would happen if I did not move missing values up and out of the category of no information. In this example, I may interpret no, cannot calculate as the exact same definition as I have nothing to guide me toward preponderance of one to the other. Okay, so so we have the visual just to complete the picture, and this is probably the simplest scorecard you'll ever see in your life, but my simple 2-variable scorecard of implementation. I have a record that has a value of 45 and a value of yes for predictor 1 versus predictor 2. I can score out record 45 yes by first grabbing the intercept, 10 point, then finding 45, awarding the 40 points for predictor 1, and finding my yes value and awarding the 40 points, remaining 40 points for predictor 2. In contrast, my scoring of record 24 unknown also receives the 10-point intercept, 10 points only for being in bin level 0, 25 points for being in bin level 2, down in predictor 2. The visual aspect is particularly helpful, especially for non-modelers. Looking at this, I can get a very quick view of things like which one of these predictors is going to have a stronger and more effect in my final score. If I look at what is neutral points for each of these two, 35 neutral points for predictor 1, 25 neutral points, you can think of that as average. How tightly wound around that average the score range is will clue me into how much or how little of an effect will this predictor have on my final score. And it's also a nice visual to understand low negative relationships versus positive relationships. And if I did have that S shape, I could see that as well. If I did have bimodal shape, I can see that all in the weights values themselves. Good. So just a quick recap. When we use the binned approach, we can visualize the relationships, especially helpful when we are dealing with a binary target. We can capture in the solution nonlinear relationships. And the generalized approach is beneficial on both the predictors, discrete and continuous, as well as targets, binary and continuous. It elegantly handles outliers, as well as missing values and special values. And there's also a nice way to support any kind of regulatory constraints that might be passed on you. And in the end, generally readily interpretable models all leading to improved analysis and improved productivity. Okay. At this time, I'm going to take questions, and I can see there's already one up. Are there any disadvantages to using binned predictors? So, of course, we, like everybody else, are evaluating all of the different options for things like machine learning models. And what scorecards have a difficult time doing is capturing the non-intuitive and non-readily visible interactions. So as we go forward with how to improve what we do, we're evaluating everything, as I think everyone is. And I would probably point to that's what we're trying to capture and add to a process is higher interaction models that really only a machine learning model might be able to identify and address. What is the best way to optimize the bin boundaries to generate best predictive accuracy? In the tool that I use, when I was at InfoCentricity, it was called Zeno. Now here at Fair Isaac, it's called Scorecard Professional. We created an algorithm called Break and Heal. And what it does is it goes through just that, an algorithm that creates bins, deletes bins in a very iterative fashion. And its quest is to, in a binary target situation, its quest is to maximize information value. Okay. We have a question about an alpha predictor. I'm not familiar with the term. All I mean is you can have predictors whose values are numbers. Those numbers can have ordinality to them. It could be a continuous predictor, or they could actually be numeric values that translate to a very discrete meaning. It's a category. I fit in category 1, category 2, category 3, but 2 isn't 1 greater than 1. It's just categorical. If those are not numerically captured, but they're captured with an alpha character, category A, category B, category C, you still have that idea of discreteness, but just captured in a different way. Continuous target. Hold on a second, I'm going to read this. I'm not quite sure I understand the question. So how does this work? Let's see. Okay, let's go back to here. Is it true that binned independent variables are more powerful for binary targets? Can you elaborate a bit on the relationship between scorecard and decision tree model? Are they more powerful? When you are, so I'm thinking of, even in the tool that I use, I can use continuous variables in their binned format, or with just a check, I can use them in their continuous format. Where binning provides lift is when the relationship between the two is nonlinear. I can see many continuous variables have a monotonic increasing or decreasing relationship as I look at the weight of evidence in the binner, but it doesn't concretely say that this is a linear relationship. So my decision to use one or the other, am I going to use the binned version, am I going to use its continuous version, is wholly reliant on whether that relationship is not just monotonic, but that it is linear. Oh, I see. How does this work for regression problems with continuous target, given that the individual values in the range receive the same coefficient? I have the same comment for this. Is it possible to further apply something like interpolation to improve accuracy? Yes. I would give a very similar answer. If I have a continuous variable, if I have a continuous outcome, my The benefit is going to come from me in keeping my predictor in its continuous format when I am convinced that I have a linear as opposed to just a increasing or decreasing relationship. On the variable selection, you use marginal contribution. Marginal contribution, and why not information value is the question. Information value is going to give me results in the univariate context. So now I have the individual relationship between predictor and performance. Marginal contribution, so this is what is introduced when I go from the classer to the actual scorecard and calculate the coefficients. Marginal contribution is going to take a multivariate look at things. It's going to be a metric that includes all of the predictive overlap that is happening between the variables. Okay. How do I control for multicollinearity? I more observe for multicollinearity. So if I have entered a variable into the scorecard, in the methodology that we use for calculating the coefficients, what we'll have is, let's say I put very correlated, or in the most extreme example, a complete copy of the variable. As I put one of the two, the original, into the model, and then I enter the second, what I'll see in the tool that I use, the solution that it, or the methodology that it uses in its solver, is that I will basically split the predicted content in half among the two. So as I'm taking my usual manual approach to building a scorecard, and I'm observing what lowers marginal contribution as it gets added, I can now see if something is at the top of the next candidate list. We call those the step 2 predictors. And I add a very close cousin variable, if not a copy. I will watch the marginal contribution of the variable that I'm considering drop way down. Oh, have we tried binned principal components? Absolutely. We take one step away from explainability when we use them. So still we have to back up and keep our solution in the context of the business problem. But yes, we definitely work with principal components as well. It's kind of a similar question for bin variables. Will there be a jump in the points from bin to bin? There could be. Does FICO consider using piecewise linear variables so there aren't jumps from bin to bin? We've worked with customers to help them find a solution when there are very large jumps. These would be customers who have very lumpy data, for lack of a more technical term. But yes. Let's see, I've got another one. Okay, I think I got every question in the. If I bypassed your question, let me just send it again. In my experience, as binned principal component improve model performance, everything is it depends. It depends on the data set that I'm working with. Sometimes yes. Sometimes it just steps too far away from what I'm trying to globally solve for my business partner. Our scorecard related to decision trees. Probably the biggest difference between the two is decision trees are extremely data hungry. So when you start at the top of a decision tree, think of a singular record. A record is going to take a singular path down the decision tree. Do they fall in a left-hand node, right-hand node, or if there are multiple nodes? And then once that data point passes down one path, it will not pass down the other path. In a scorecard, if you remember the picture of the scorecard that I put up, a single data element passes through every variable. So my single data element of 45 yes is not done after it passes through predictor 1, whereas in a tree, once it gets evaluated for predictor 1, it is, and it makes its way all the way down to the end of the tree. There it is. We don't glean any more information from it. We have access to the recorded video and slides after. I think that's possible. I will verify that with the moderator. Talk a little bit about how the algorithm enforces pattern constraints. How is it implemented? We actually step into the world of pattern search. So what we're supplying the algorithm is an overall mission to optimize an objective function, but then we overlay all of the pattern constraints and neutralizations on top of that, and we use a variant of the Hook and Jeeves algorithm to come to an optimal solution. How do you know when you should segment population into 2 with separate scorecards? Typically what I'll do is, a couple of slides back you saw, let me find side by side. Here, let me see if I could do this. I want to find a side by side. Sorry, something like this. This is what I will be looking for in my class. Or I will segment, I will come up with a candidate population split, and it will be warranted if I see side by side. Let's say this is not binary target and continuous target, but this is binary target for segment 1, binary target for segment 2. I'm not just looking for a difference in pop odds. Okay, so I'm not just looking for, is my rate for a binary target greater or lesser for one population than the other. I'm looking for, at the variable level, should I build a different scorecard? So is the relationship between predictor and performance different for one population or another? It doesn't need to be as egregious as this. It could be that my information value is very different for 2, or my point of inflection is very different for 2. Oh, to generate bins, can I work with the entire data set or just a sample? Absolutely, we advocate sampling as much as possible. What you'll be able to do is, you see this W for weighted, what you'll be able to do is pass, as I did here, pretty much an even sample of 2, although my population is anything but 50% divided 50% between the 2. So what I captured is a sample weight for each of all of the records. And now when I look at the percentages, the percent distribution, I can see they're factored up to the entire population rather than just my sample population. That was a great question. Thank you. It's also important for why it comes into play here. So if I'm looking at, if I've used my simplest of stratified random sampling, and I just simply stratified across my 2 performances in a binary situation, 1s and 0s, I'll be working with exactly this. Let's say I took just 10% of the 1 category and 100% of the 0 category. I'll place myself in this exact situation. So question came in that's really related to, is the algorithm sensitive to imbalanced classes? No, it's for this very reason. We've got metrics and measures that are invariant to the population odds. Okay, we are at the end of our 45 minutes, and I want to be very respectful for everybody's time. So thank you. Let me fast forward to the end. We're sending you a poll on your screen. Are you ready to hear more? Your options are, if you'd like to see a live demo, please click the radio button next to A and hit submit. If you'd like to be sent additional materials, that's B. And if you would like to schedule a call, then click C and then hit submit, and we'll have your information and we will follow up. And lastly, I'd like to thank you very much. I know your time is precious. Thank you for taking some time out today, and I hope to be speaking to you again soon. Thank you very much.